the example 1 has a extension. So you can see that extension in our slides. Okay, just look at this extension of example 1. It's a shaft and pulley bending problem. Look at that one. And just thinking about that, if this one is the same as our example 1. If you understand the nature, you will see that actually this extension is exactly the same as our example 1. I have provided the correct solution, the correct answer at the bottom of that slide. Try to work out this number by yourself. Okay, if you can get the same result, it perhaps okay. And if you get a different result and you can validate it and falsify my result, just let me know. I will give you bonus point. Okay. So now let's look at example 2. Okay, the example 2 is not very different from example 1. We just replaced the concentrated load on the simply supported part by a uniformly distributed load. Here just let's look at how to solve this one. This I didn't give any numbers for it, so we just derive kind of expressions. But anyway, so for this thing, we're determining the deflection of the point C, it's still the free end of the cantilever part. But still you can split it into 3 beams as shown here. This is the beam 1, beam 2, and beam 3. For beam 1, you just need to use a simple equation to calculate the deflection delta 1. And for beam 2 and beam 3, you just calculate these 2 theta values and use these 2 triangles to find out the other 2 components of the deflection. Then add them together, it will solve the problem. Okay, let's look at the beam 1 first. So beam 1. So here again, we have been using equation 20 to solve this kind of problem, right? So from equation 20, we know that the delta 1 can be calculated from the P L1 cube over 3 EI. It's negative, right? Negative, this will be downward, a downward deflection. So this will be negative P times, since the L1 here is L over 4, right? It's L over 4 cube over 3 EI. That will be negative PL cube over 192 EI. This will be a downward deflection. Right. So we're done with beam 1. Then let's look at beam 2. So the beam 2, as shown here, is a simply supported beam subjected to a uniformly distributed load. Let's call it W. Okay, from the table, let's look at this table and find the equation. A simply supported beam, uniformly distributed load here. Then we're calculating the slope at the right end. Right, there's the left support and right support has 2 slope, and the slope values have the same magnitude, or just one positive, one negative, and it will be a negative in the right hand side, in the left hand side, and positive value at the right hand side. Right, but the equation will be the same. So here from equation 10, right, we're using equation 10. So here the theta 2 can be calculated by W L cube over 24 EI. So the deflection delta 2 prime will be just in this triangle, right? So here is the triangle and we have known this angle equals theta 2, and you have known here this is BC, right? And we suppose this is a small enough angle, so this delta 2 prime just equals BC by theta 2. And the BC is L over 4 by WL cube over 24 EI. And this will be W L to the 4th over 96 EI. And this is upward deflection. Then beam 3. Beam 3 is subjected to a simply supported beam subjected to a bending moment M, and the M is P by BC, right? PL over 4. This is the magnitude of this bending moment. So the M equals PL over 4. So again, strictly speaking, it should be a negative bending moment, since it will make the section AB cry. Right? It's a negative value, but we do not care about the sign here. We just use its magnitude for the calculation. But now let's look at the equation, the correct equation to calculate this problem. This will be, again, 7. And equation 1, so as we analyzed in example 1, right? Just use this equation. So here the theta 3 can thus be calculated as negative ML over 3 EI. And this is a negative, just use this number here. Right, it's a negative PL square over 12 EI. So based on this, the delta 3 prime can be calculated. Right now we're looking at this triangle. Right, here the angle is theta 3, and here the BC. Right, so this equals BC by theta 3. And it will be L over 4 by negative PL square over 12 EI. This is negative PL cube over 48 EI. And this is a downward deflection. Okay. So in the end, to summarize, the overall deflection at point C can be calculated from, we just sum the 3 components together. Right? We have delta 1, delta 2 prime, delta 3 prime. Then the first component is here, second here, and the third is here. Okay, so we'll have negative PL cube over 192 EI plus WL to the 4th over 96 EI. Then it's a negative again. Minus PL cube over 48 EI. So you can do further calculations to get a result, just in a form that you like. Okay, you can do this by yourself. But overall, this will be a downward. Very likely, it will be a downward deflection. Okay. Well, in this example, just we showed again how to calculate the deflection at the free end of the cantilever part. Then how about the middle span point of the simply supported part? Okay, so I will give you a in-class assessment. Okay, only when you watch this video to this end, you know that we have a in-class assessment, and I tell you that the in-class assessment, you need to find it out. I will upload it to the folder of chapter 5, okay, not chapter 6. You just need to go to Canvas and open the folder chapter 5 and find this problem for the in-class assessment. I will name it lecture 18 in-class assessment. Find it out and work it out. Then you can submit it through Canvas. So I will give you a link to submit it. Okay, just do it by yourself and upload it, and I will record this point for you.